Hi everyone, we're Team Fantastic Four. Our project is houses detection using computer vision and machine learning methods. Next, please. Our goal is to accurately detect houses, which includes object classification and detection problems, and we emphasize on learning structures of houses. We used a mix of machine learning and OpenCV algorithms, and we tested the capability of algorithms to accurately classify and identify houses. To identify houses using learning methods in OpenCV and machine learning, first we input a stream of house images and non-houses images, and the output depends on the problem. If it's classification, it's 1 or 0. If it's detection, then we will have a bounding box with or without segmentation of the house. Then we use human evaluation and accuracy metrics to assess the quality of the output.
For the dataset, we used open source SoCal images, which consist of over 15,000 house images. While for non-houses images, we used Open Images dataset and MIT CSAIL images. For our methodology, we used a bunch of algorithms which involve local feature matching and supervised machine learning. The local feature matching involved the algorithms implementation of SIFT, SIRF, and ORB, while the machine learning methods include CNN, mask, RCNN, and Haar cascade classifier.
So the local feature matching answer the question, if I know my grandma's house, how do I find her house in a picture? So first we take out the object and use it as the query image. Second, we use SIFT, SIRF, or ORB to extract features in grayscale image. The outcomes are the key points and descriptors. Then we match the descriptors using 2 nearest neighbors and use Lowe's ratio rate to decide if a match is good enough. Finally, to identify the contour, we use homography to map the points in the query image to the corresponding points in the training image. Next, please. The first 2 rows are the time spent on feature extraction and the amount of key points in the query image. The key points 2 are the key points in the training image. So based on the first 3 rows, ORB is the fastest and it can detect more key points. All the key points in the object image can match 2 key points in the training image, but very few of the matches have high quality based on Lowe's ratio rate. We can tell SIFT has the highest good match rate, and all these 3 methods can perform well after we blurred, rotated, and scaled the original image. Next, please. From this table, we can tell ORB is still the fastest and extracted most key points, and SIFT has the highest good matching rate. All the methods performed well on a different image of this house observed from a different angle. Next, please. This is a different case. So based on the 3rd row, SIRF is not faster than SIFT, which is strange because SIRF should be fundamentally faster. There might be a lot of noise in the processing time. And ORB is still the fastest. And SIFT extracted most key points in this blurry house object and has the highest good match rate. ORB failed to render a bounding box because there aren't enough good matches, but it can still find the right houses. Based on all of our experience, SIFT is the most robust algorithm. Next, please.
We are using a deep neural network for our image classification model, which is a type of artificial neural network that contains multiple hidden layers. The convolutional neural network was the deep neural network we chose for our project, as CNNs were designed for processing pixel data, making it efficient at image feature extraction compared to similar model types. The exact structure of our CNN was influenced by VGGNet, which includes groupings of 3x3 convolutional kernel layers followed by max pool layers. While not identical, our CNN is comparable to this setup. Next slide, please. So a quick note before getting into the results. The input images we used for training and testing vary in levels of occlusion. For example, our non-house category included images of non-house buildings, while our house category included houses that are partially obscured. This noticeably affects our results, which we will get to shortly. Please continue. So here's a quick overview of the architecture of our CNN. We have our 415 by 311 pixel input image, which has been grayscaled to remove color dependency, followed by an initial max pooling layer. We then have two sets of two convolutional layers, followed by max pooling layers, followed by a fully connected layer of 256 neurons, a 20% dropout, and then our two-class classifier layer as our output. So here's a quick overview of the data we got from our training, testing, and validation data. We achieved approximately 91% training accuracy, 85% validation accuracy, and 81% testing accuracy. Please.
So the next neural network we used was mask RCNN. It operates in two phases. The first phase is proposal generation. A backbone network converts the image into a feature map. So it takes the whole image, makes a roughly 38 by 38 by 2000 feature map that has the various edges, but also outlines objects inside of it. And then a region proposal network produces proposals around each of those places of interest in the feature map, determining whether they're in the foreground or in the background. Then in the proposal classification and mask generation step, an ROI classifier determines the proposal object classes of all of the foreground objects to determine whether they are houses or not houses. And then an ROI pooling method runs to crop those feature maps and resize them to make sure they're all the same size. Then at the end, segmentation masks are generated for the regions, such as the one shown in the bottom right-hand corner. And that mask shows the overall outline of the image. Next slide, please. So our implementation of mask RCNN, we cloned the GitHub repo from Matterport and used the MS Coco pre-trained weights as a basis, since MS Coco was trained on a large set of objects. Then we trained it further on 75 house images to specifically make the model look for only houses in images. So we took a JSON of labeled mask outlines for the houses, as shown to the top right. That's one of the house outlines. And using that as the annotations, we trained 30 epochs with 10 steps per epoch to update our model. Then afterwards, we validated it on 20 hand annotated house images and found that the model works quite successfully in identifying houses, as seen to the bottom right, where the house was detected with an accuracy of 0.989, and it shows a full nice outline. Next slide, please. So unobstructed houses get detected very effectively with minimal interference. However, obstructed houses show the house's different components as different house chunks. And while the house behind the obstruction is still detected, sometimes the obstruction is included in that house detection. However, overall, the house was detected in full despite obstructions. Next slide, please.
Haar cascade is another machine learning based approach used for object detection. It is based on a cascade function which is trained using positive and negative images. The positive images include images of the house which contain relevant features. Haar cascade is a sequence of a scaled square shape function which essentially follows the same principle as of convolution kernel. These features are computed using edge, line, and rectangular feature as in the figure described below. A small video demonstration of how the features are obtained as a single value is shown on the right-hand side. This calculates and determines the relevant features, which construct the classifier as a linear combination of weighted inputs. The Haar classifier works on retrieving the features. Even for small images, we would get over 160,000 features. Hence, to extract the relevant and essential feature, we used AdaBoost, which finds the best threshold to classify between positive and negative images. The cascade classifier helps to group the relevant features and apply it one by one. The sum of values of weak classifier is compared with the threshold of cascade classifier, and a decision is made whether the desired object features are to be found or not. Below, we can see an overview of Haar cascade classifier architecture. And on the right, we can see the extracted features which were obtained while the algorithm was training. To look at the results, we can see the Haar cascade classifier is able to recognize the key features of the houses, like the roof. On the image on the right, we can see the bounding box represents the houses, but it is not classified properly as it was trained on a image data set consisting of less images. When I trained the data set on a larger positive image, I was able to get much better results, as you can see on the left-hand side.
So for a quick overview of our method results, for local feature mapping, we concluded that SIFT was the most robust option of the three, due in part to the lack of training needed. For machine learning, we found our results suitable for non-specific house detection, but it was difficult to compare these results with those of local feature mapping due to differing output metrics. Next slide, please. There were a few limitations to our methods. A couple of these included the effect of obscuring features and the effect of the overlap of desired features. Go ahead.
In conclusion, we successfully compared neural network architecture and OpenCV methods for classifying and identifying houses, and found that due to the different outputs of each method has different applications it's useful for. So potential future work could involve testing using video input to identify houses, identifying particular types of houses, and combining feature matching methods to ensure object bounding. Next slide, please. These are our references, and thank you so much. What are the questions?